passed in everything, and preferably everybody should get a first class. It will not happen. Everybody will not get a first class, but everybody should attempt to get a first class so that in this bad market, they have a better job prospect. That's all I'm saying. How many have come? Akshay is there. Your CR.
Sir, no, he's not there. 6 people are there, sir, present.
7 are there.
Yeah, sorry, sir, 7.
7 minus Sagar and me, right?
Yeah, sir, counting you all, they are total 9.
Okay, good. Yeah, you always subtract 2 and tell me. So we wait for another few minutes or what? It is 11:04. So Karan will start, let others join.
Yes, sir.
Okay, so I went back a couple of slides and you can see in this slide on the equipment part, okay, at the somewhere in the middle it is written that in clean reservoirs containing little or no shales, the neutron log response will provide a good measure of formation porosity if liquid filled pore spaces contain hydrogen, as is the case when pores are filled with oil or water. Okay, and within bracket it says hydrogen index 1. What is the meaning of that? So meaning of that means the hydrogen index means its definition is nothing but the weight percentage of hydrogen in the formation. Suppose you have a formation and you find out the weight percentage of hydrogen in the formation and you divide by the weight percentage of hydrogen in water or oil, then you get the hydrogen index 1. Is that clear? So the weight percentage of hydrogen present in the formation divided by the weight percentage of hydrogen in water or oil, whatever it is, preferably water, is equal to, is the definition of the hydrogen index. And if hydrogen index is 1 means it's perfect. Perfect means, I showed you that here. You remember when there is hydrogen, 18 collisions are required for the neutron to lose its energy from 2 MeV to 0.025 electron volt because it is elastic. Whereas in the case of chlorine or calcium, look at calcium, okay, it is 368. It needs 368 collisions to decrease from 2 MeVs to about 0.22, 0.25 electron volt. Is that clear? So we defined the hydrogen index. Where did I define? No. Where did I? The hydrogen index 1 is, you have understood the definition? The weight percentage of hydrogen which is present in the formation, okay, divided by the weight percentage of hydrogen which is present in water or present in oil. Because water has oxygen also. Oil has hydrogen and carbon also. So depends on that. its hydrogen index 1. That is the definition of hydrogen index 1. Is that correct? Have you understood it? That's the definition that we talked about. Okay, when we were discussing what is called the litho density tool. Okay, we said that the litho density, that means the P value, was equal to the cross section divided by the bulk density, rho B. Remember I told you that or not? Karan, hello, hello, hello.
Yes, sir.
Asma,
Yes,
you
sir.
remember the definition? I told you that the litho density, the P is equal to U, which is the cross section of a particular element divided by the bulk density rho B, which we get from the gamma gamma density law. You remember that or not?
Yes.
Okay, you can always go back to the books, Ryder or Osera or whatever, or Schlumberger, and find it out. So it is a function, the P value was a function of the cross section of the elements. It's the same thing. The neutron log is also a function of the cross section of the elements. It is a function of the cross section of the elements because of the absorption coefficient. Just like you had in the photoelectric, we called it as the absorption cross section coefficient. Here it's also the absorption cross section coefficient. And the absorption cross section coefficient of hydrogen is 0.33, oxygen, carbon, they're very small. They're of the order of 0.00, 0.12, whatever it is. But when you come to something like, boron or something like that, it is 759. Just like we had, for what we had 1079 for which element in case of P value, you recollect that? Barite, you recollect?
Yes, sir.
Yeah. So Samir has finally joined in. So we had in barite we had a very large cross section. So that's why in a borehole, if you have used barite, then the litho density, the LDT tool to use becomes difficult. Similarly, in neutron log also it's a function of the absorption cross section of these elements. And normally all these hydrogen, oxygen, carbon, they are very less. But if you go to something like boron, it's 759, and if you go to cadmium, is very high, it's 2450. The cross section of cadmium is 2450. Okay, for boron and all, it is very high. I said 759, whatever. But luckily, this the element boron is normally not found in nature, so you are safe. Is that clear? So here also the absorption coefficient of the element plays a role in the absorbing or the collision of the neutron. Is that okay?
Yes, sir.
Okay. Then on the top we said what is a neutron logging tool? Here we have plutonium, beryllium, or americium, beryllium. Unlike cobalt, which is naturally occurring, cobalt 60, or we had cesium 137. It is also naturally occurring. That's why you have them in the periodic table. So cesium 137. But this plutonium, beryllium, or americium, beryllium are chemically made. They are chemically made. So they are chemicals. Okay, they are made or artificial, whatever you can call it. So they are artificially made. So that's one of the difference between the source of the gamma gamma density log and the neutron log. Is that clear?
Yes, sir.
Very good. So what is not if you look at if you, let's say you had a hydrogen and we said, for example, we said when we go back, and if it's hydrogen, we said 18 collisions are required to slow it down from 2 MeV to 0.25 MeV, right? But if you had calcium, You need 368 collisions.
368 collision.
Yeah, so why? Because one is elastic, the other is inelastic. And we said the neutron has the same mass as the hydrogen. Didn't we say that? Is that clear?
Yes, sir.
Then we also said that we are going to use a source which is given here with 4 MeV, whether it is plutonium, beryllium, or americium, beryllium, whatever. We said it is 4 MeV, it's a high, and we said that initially it emits fast neutrons, then it emits what is called as epithermal neutrons, and finally it goes to the thermal neutrons. And of course, the energy will decrease from 4 MeV to whatever, maybe 0.22 electron volt. I had shown you a diagram which was not very, yeah, look at all this. So it goes almost, from about 10 to the power 6. By the time it goes to thermal, it is almost 0.04 energy. And the velocity is from 2200 centimeter per microsecond, it goes down to 0.22 in the thermal range. Okay. And the epithermal range, it is 2 point whatever, 2.2 or 2.3. So,
2.
yeah, so you have to remember that. Okay, so that's the important. So it says neutron lose energy with each collision. Okay. Then we talked about all these neutrons are slow sufficiently to be captured and all those type of things. And then it says depending on the type of logging tool, either gamma rays or non-captured neutrons are recorded. Okay, there is also another loop called neutron capture log. We are not going to talk about that. So that takes this neutron captures. So what happens is the neutron, when it loses energy, it diffuses till it's captured, and then one electron or photon is released, and then there's a separate logging tool which is called the neutron capture logging tool is talking about that. So we are not going to talk much about that. So if hydrogen in pore spaces, porosity is related to the ratio of neutron to those captured or as captured. We don't talk. Okay, now we come to this. We said, if you look at it, we have all the tools on the left-hand side, the name. Let's take the very first top one. It says compensated neutron log. And the company, you forget, Schlumberger, but it says the detector is so it's working on the thermal. So almost everything is majority of 1, 2, 3, 4, 5, 6, 7, 8. Out of 9, 1, 2, 3, 4, 5 of them are working in the thermal, and almost the remaining 4 are working in the epithermal. None of them are working in the fast neutron. None of them are working in the fast neutron. So when we go back to the diagram that I showed you, yeah, so none of them are working in the fast neutron part. 4 or 5 of them, some of them work in epithermal, but the majority of them are working in thermal. Is that clear?
Yes, sir.
Okay. The next question is why? I don't know whether this is the example. So you have the high energy neutron source and the collision causing slowdown, and you have this capture that we talked to you on. You have the gamma ray that reaches the thermal from the epithermal to thermal range and whatever. And it's the same thing, 10 to the power 5 electron volt, and finally it comes down, and you can see most of your logs are in the thermal, the CNL, the SNP, which is the sidewall neutron probe. They all work at low energy level. They are all working at the low energy level. That's what he's talking about. But my question is why? My question is why? Why are we not using the fast neutrons? Why are we concentrating on the thermal or the epithermal? That's what we said in this graph, right? On this graph. Is that clear? This graph is clear? Samir,
Yes, sir.
look at the graph right hand side. The tools are almost in the energy of thermal energy level.
Yes, sir.
Right? So why? What is the reason for? What is the tool? What is the receiver we are using in the case of neutron? I told you the other day on Tuesday. What is the receiver you are using? Asma, what is the receiver you are using? What is the receiver you are using in gamma gamma density law?
Scintillation counter.
Scintillator
Huh?
count.
Scintillation counter. What is the receiver you are using in neutron law?
Beryllium, sir.
What is the receiver you are using in LED, the litho density law?
Beryllium, sir.
Beryllium window, re Baba. It is a scintillation counter. It
Yes, sir.
uses a
Scintillator
beryllium
count.
window so that the energy, low energy moves in. So it's not beryllium, it's a beryllium window. Is that clear,
Yes,
Samir?
sir. Yes, sir.
Okay. Now what? So basically, it's a scintillation counter again, but it has got a beryllium window so that it catches only the low energy level. What is the receiver we are using in this neutron log, which I told you on Tuesday? Asma, everybody after the class, usko band karke, they tune
Limestone,
on
sir.
to the, huh?
Limestone.
No, no, receiver, re Baba. What type of receiver?
Plutonium, beryllium, sir.
No, that is a source.
That is a source, sir.
Receiver ka पूछ रहा रे Baba. I
Receiver.
told you, you are going to use a receiver which has helium gas. The detectors are having helium gas. Didn't I tell you that?
Yes, sir. Yes, sir. Helium gas.
Uh, 3HE, what I said. So you are using a helium detector or helium gas detector in the case of neutron law. So this helium gas detector, what it does is these photons or these gamma rays which enters into this helium gas, it ionizes and then only it detects it. So there is a process of ionization also which takes place in the helium gas, and then you get the count. Is that okay?
Yes, sir.
Okay, now this efficiency of this ionization gas or the helium gas detector that we are using is inversely proportional to the energy level. That means it is very, very efficient when the energy level is small. It's very, very inefficient with the energy level of the neutron is large. So if the fast neutron has a lot of energy, it's very inefficient, and it is very efficient when the energy is very small, so if it's in the thermal range. So that's why these helium detectors which are used in neutron normally work in the thermal range. Is that okay?
Yes, sir.
Have you understood it very clearly?
Yes, sir. Yes, sir.
See, Samir, there are two reasons that I don't know whether you were there when Karan and Asma were there. In case there's an exam going to be held, and I don't know what the Pune University is going to decide, but if there's going to be an online examination, okay,
Yes, sir.
then obviously it will be one of those multiple choice. That means you give yes, no, or you give 1, 2. The answer is yeah, 1, 2, and within 1 hour you know your results, right?
Yes, sir.
So in that there is no question of could be, would be, and all that thing that you told. For receiver, you told me source and things like that. You be very focused and understand. Receiver means receiver. There's no question of when I'm asking a receiver, you're talking about a plutonium beryllium, which is a source. If I'm asking a source, is source. If I'm
Yes, sir.
asking, okay, is the source in neutron log artificial or the one used in gamma gamma density log artificial? What is your answer? What is the answer?
What, sir?
Is the source which is used in gamma density log is artificial, or the source which is used in neutron log is artificial.
Sir, neutron log is artificial.
So like that you should be able to tell the pinpoint answer, then only you'll get the score. Is that clear?
Yes, sir.
Okay, so have you understood that unlike the
Yes, sir.
other detector scintillation counters, the neutron which is having the same mass as hydrogen, okay, and helium gas, it is nothing but an isotope of hydrogen, it is 3Hg, is an isotope of hydrogen. In order for it to detect the neutron, okay, which
Neutron.
collides with the hydrogen, it has to be ionized in the gas. So because of that ionization process, it's inversely proportional to the energy of the neutron which is coming in. So the slow inversely proportional. So the thermal neutrons are more, for thermal neutrons the ionization, the helium gas detector is very sensitive, whereas for the fast neutrons it is not that sensitive. Is that clear?
Yes, sir.
Okay. Now, now for example, let's say you have this. Now you have this, right? I showed you this, right? Now you have one, two, let's say three, four, five of them is thermal,
Thermal.
and one, two, three, four of them are epithermal, right?
Yes, sir.
Leave aside that dual neutron, wo chhod ke, okay, then you can see there is an equal balance of thermal and epithermal. If you leave that, you have one, two, three, four of thermal and four and epithermal, right?
Yes, sir.
Okay. Now question is, if I want to detect epithermal, how do I get rid of the thermal? If I want to detect epithermal, just like you used the beryllium window in the LDT log, the litho density tool, so that you could get the low energy, the gamma rays. You recollect? We did that. We made a window. We had
Yes, sir.
similar spectral windows in case of spectral gamma rays, so that we could find thorium, uranium, and potassium peaks. So if I want to detect the epithermal, how do I get rid of the thermal? You understood the question?
Yes, sir. I understood. I'm
हाँ
thinking, sir.
हाँ थिंकिंग करो थिंकिंग के लिए पूरा दिन मत लगाओ एक मिनट लगाओ A few minutes ago what did I tell you? That just like your litho density tool, the neutron is also a function of the cross section. Didn't I tell you that?
Yes, sir.
Cross section of the elements.
Cross
And
section
I
of the
told
element.
you, yeah, just like your litho density, you had a
Litho
barite
density.
which was 1079 or 1076 cross section or whatever it is, right? You recollect that?
1074, sir.
74, whatever. You recollect that?
Yes,
So,
sir.
in a hole where barite has been used, you could not use the LDT tool. And that is why one of the reasons that LDT tool is not very commonly used.
Commonly used.
I told you that. You recollect?
Yes, sir.
Okay. Now, in this particular case, I told you the cadmium has a cross section of 2450. The cadmium has a cross section of 2450. So that means if I have cadmium, then it cannot go through it. Am I right?
Yes, sir.
The cross section is too large.
Too
So
large.
if this helium detector, I can put a cadmium coating on it, then obviously the thermal will be stopped. You get the idea?
Yes, sir. Yes, sir.
So I can stop the thermal, or I can allow the thermal by playing with the coating, by coating it with, just like you have a radioactive element, okay, and let's say you are going to carry it from Pune to Bombay. You have a cobalt 60 source. How you are going to carry it? In your purse? How are you going to carry it? Radioactive. How is radioactive source carried? Asma,
Yes, sir.
how is radioactive source carried from one place to another, or where? How is radioactive source kept so that
And
you
that
don't get
is
exposed?
enclosed in heavy metal coverings.
What is that heavy
Usually,
metal? You have to tell me. Iron.
uh,
What
I
is it?
cannot recall at this moment, but I know that it has to be kept heavily insulated in a.
Yes, you're right, but I need to know what it is. You are very correct on the answer, but you're not able to answer the question. I asked you because you did all that in the lab. I don't know whether
Yes,
you've
sir.
seen it in the lab, but you've been in a lab. So normally it is always taken in lead, in a lead container, PB, lead. It is taken in a lead container so that the radioactivity which comes out of this cesium 137 cobalt, whether it's zero point 0.5 curie, 1 curie, it doesn't, these gamma rays doesn't get into your body. And when you want to take it out and put it in the sun, you have to wear a badge to see how much of radioactivity you have been exposed to. Is that clear?
Yes, sir.
Asma?
Yes, sir.
So lead is the one in which it is carried. Samir, you understood?
No, sir.
Array, if you are carrying radioactive element, any radioactive element from one place to another, you normally will put it in a lead container.
Lead container.
Yeah, you will normally put it in a lead container so that the radioactivity, the gamma rays which is emitted from the cobalt or cesium 137 or any thorium, uranium, potassium source doesn't affect your body. Otherwise, you will die. You will be exposed to radiation, right? Your cells will be damaged. Is
Okay,
that
sir.
clear?
Yes, sir. Yes, sir.
So it's carried in a lead container. So that means it's like cutout. It's like a
Cut.
cutout,
Yes, sir.
right?
Yes, sir.
Similarly, in the case of if you want to use epithermal, I cut off the thermal using what is the cadmium in this particular case, because the cadmium has a very high cross section,
Cross
absorption
section.
cross section of something like 2450. Is that clear?
Yes, sir. Yes, sir.
So I made it very clear why you are using helium gas 3He in the detector, and the two processes goes through ionization comes scattering, and then finally why we are working in the thermal or epithermal range rather than in the fast neutron. Is that clear?
Yes, sir.
Very good. So, most of these logs, the neutron logs, are either run with density, gamma, and caliper. So they normally run with density, gamma. So oftentimes you will see an FDC, we said fully compensated density log, or just now we said a compensated neutron log, or we talked about the litho density log, and so forth. So they're normally done in combination with these things because you need cross plots to find out the porosity. Is that clear? Of course, we have the caliper and the gamma ray always.
In compensated
Okay?
log, sir.
Huh?
On compos on first track one, sir.
Yeah, what I'm saying, you normally run this neutron log, density log, and the litho density, whatever you can call, they are run together.
Yes, sir.
So you run a CNN log, an FDC log, or an LDT log, and a CNN log like that. You understood?
Yes, sir.
That is what I'm trying to tell you. And you always have the caliper and the gamma ray log in the first track. Is that clear? So we talked about all this. You recollect we talked about all this?
Yes, sir.
Okay. So we talked about this is the same thing. We talked about all this. Here is that helium detector which I was talking to you about. So helium means H3. It's an isotope of hydrogen. It's helium. Okay. Is that okay?
Yes, sir.
Okay. And what are the other names for these neutron logs? Neutron
Limestone
log
curve
can be,
log.
huh?
Limestone curve log.
And what else?
Hydrogen index log.
What else? Let's see whether Samir can answer this question.
Both two are, sir. Hydrogen index
Why?
log and limestone curve log.
Cannot be a third one from the
No,
common sense? Why?
I just heard about two names, sir. Hydrogen index log and limestone curve log.
Hydrogen index log and this thing. Now, let's say, Samir, that one company who is working in groundwater, okay,
Yes, sir.
offers you a lot of money and you don't have a job from a hydrocarbon company. So obviously you will join this groundwater. Am I right?
Yes, sir.
Okay. Now if you are working in this groundwater exploration company, whatever, they are not interested in a hydrogen index, HI, neither they are interested in limestone. They may be interested, but normally not. So what are they interested in? The water.
Water, sir.
So water means what? What is the other name for water?
H2O, sir.
अरे H2O तो उसको केमिकल कॉम्पोजिशन हो गया रे बाबा.
Yes, sir.
It is the other name for this neutron log is called the moisture log. Moisture is the amount of water. You remember we said that it is very sensitive to water which is either present in the crystalline form, in the liquid form, or in the bound form. Didn't I tell you that?
Yes, sir.
I showed you, if you recollect. So the other name for a third name for neutron log is also called the moisture log. Is that okay? Moisture means water.
Yes, sir.
Though it is sensitive, equally sensitive both to hydrocarbon and water because both of them have H. But I told you the hydrogen carbon index is equal to 1 when the weight percentage of hydrogen present in the formation divided by the weight percentage of hydrogen present in water or oil. In water it is H2O, and in normal a long chain hydrocarbon you have HCCH or whatever it is. So it depends upon the hydrogen present. So if H is equal to 1, that means it's definitely water. If H is equal to, it could be oil also, but it will be normally definitely water. If H is not equal to 1 or close to 1, it could be present. It could be due to oil, that is long chain hydrocarbon. Is that clear?
Yes, sir.
So then I think we had stopped somewhere here. We were talking about this yesterday and we said that the American Petroleum Institute Neutron unit used by all service companies and 1000 API unit is the difference between neutron tool reading without a source, that means background level. That means I have a layer in which there is no neutron in that, and with a source and the one which is with a source. Okay, that means it is having this radioactive source of neutron. The same thing we did the calibration for this natural gamma ray log when we did at the University of Houston. So how it is done? It contains 3 reference blocks, whatever the details is given. It is given also in your rider and all. 77 by 8-inch hole drilled. Okay, 1000 API corresponds to when the tool is in the middle, 19%. So they have, if you can see it very clearly, there are 3. One is having Carthage marble, which is having a 19% porosity, and I see Indiana limestone, which is having a 19% porosity, and I have a Austin limestone, which is having, I don't know, 26 or 28% porosity. So you have 3 of them. So that's what it's saying, 3 reference blocks. Okay, and then above it you have above the Carthage marble you have what is called you have concrete. Yeah, you have a concrete and fresh water right on the top. Okay, so what it's saying is when you are doing in this 3 of them, that is the Carthage or Indiana or Austin limestone having different porosity, 19%, 26% or whatever, you try to take the reading when it is in the middle part, in the middle. Okay, so 1.9 Carthage marble block used in conjunction with 1000 whatever porosity. Modern neutron logs are scaled directly or hydrogen. So you try to find out at the middle of it what is the deflection, and then you come up to the fresh water or the concrete on the top where the radioactive source is not there. You see the deflection, and 1 by 1000 of the deflection refers to 1 API unit. That is what it's talking about. On the right hand side, you have the hydrogen index. You have the, let me see, oh, I can't see it. Okay, it's you can see limestone. We said the limestone which is fresh, that means it is not having shale or whatever, and it is having fresh water, is the standard, which is in the middle. And then you have the sandstone and you have the dolomite. You have the dolomite and you have the sandstone. The hydrogen index is given at the bottom, and on the x-axis it says real hydrogen index for the indicated matrix, whatever. And the dashed line and the solid line refers to the compensated neutron log or the sidewall neutron log probe. Okay, so what is telling you that limestone is the one, it's 45 degree, it's the one which we use for calibration because it is fresh and it is with fresh water. That means, sorry, it is clean, not fresh. It is clean and it is filled with fresh water. Whereas the sandstone and the lime dolomite, how it compares with the limestone is given, and with respect to the hydrogen index. It says the neutron tool responds to the volume of water. We already told that, right? The neutron tool is talks about the hydrogen index, talks about the moisture or whatever. Okay, it talks about the hydrogen. So neutron tool responds to the volume of water. The moment you have a water, it's referring to the volume of water. It could also refer to the volume of oil, but normally it is referred to the volume of water. Calibration is required for calculation as matrix materials have different effects on the neutron log with change in porosity. So what is saying? Why is the calibration required? It is required because the matrix materials have different effect on the neutron log with the change in porosity. You could have a change in porosity. So that means if you have a change in porosity, let's say 19% porosity or a 26% porosity, whatever, there could be a change in porosity. There could be also a change in the fluid. For example, you could have a gas field, you could have an oil field, you could have a water field, whatever it is. So the calibration is definitely required. A water-filled sandstone with 20% porosity gives a different neutron log reading to water-filled limestone with 20% porosity. So both of them are having 20% porosity. Both of them are having 20% porosity, but one is a sandstone, the other is a limestone. And we said that the neutron log normally is sensitive to the amount of water, right? We said that is hydrogen index or amount of water, which is written on the top. So theoretically, it should have given that same, but no, it's also a function of the lithology. So it's a function of the fluid, it is a function of the porosity, it's a function of the lithology. On the bottom, you can see it says log 5. 5 is the porosity with base to the 10 is equal to A into N plus B. A and B are constant, and N is, I'm sure it's derived from the neutron. I can't read it. Okay. Okay. N is derived from the neutron log. So you have the neutron porosity which is coming in, and you correct it. You have the constants A and B after calibration. From there, you get log to the base 10, you get the porosity, the true porosity or phi. Okay. So just like we remember in the case of density log, we said that you need to know the matrix density, you need to know the fluid density, and you need to know the bulk density. And the bulk density you get from the density log, but definitely you need the matrix density. And we said the matrix density you get in the lab or from the wellhead, that means from the mud logging. And we said, okay, you can take normally for fluid as 0.7. And so you calculate the porosity. You recollect all that?
Yes, sir.
Yeah, so it's the same thing here. So here is the compensated neutral log values plotted against core porosity values. So this is a plot of, I'm not able to see very well, but it says, let's see, on the y-axis it says, what is that? I can't read it very carefully. You can read it very carefully.
compensated
Anyway,
neutron limestone for porosity.
no, on the y-axis क्या है लिखा है? Y-axis, left axis.
Sir, core
The,
porosity.
The
the
core
bottom axis
porosity.
is,
Core
huh?
porosity. Core
Okay,
porosity.
so core porosity means you have a core.
Yes, sir.
I'm sure Pradeep or somebody must have talked to you about core analysis,
Yes, sir.
and you heard that Asma's lecture or whatever, her experience when she worked in the core lab or whatever in the lab. She talked about core a lot. So when you have a core which comes out from the mud logging or whatever it is, and you can find its porosity, okay, and you can find out the compensated neutron porosity, and this is the curve that is talking about. So if you have if you have one, you can get the other, is what is talking about. Okay, and it says that what is say this curve is talking about something. What is it talking about? It has some relationship. Phi is equal to some relationship you get. So if you can plot between the dense core and the neutron log, you can get a relationship. So for an unknown area, unknown borehole in the same area, you can apply the relationship, which is given, which I'm not able to read. Okay? And this is taken in the West Permian Basin and is taken, and the density is 2.84 to 2.88 grams per cc. Then we come to the log presentation. So this anyway, this has gone up. Don't you can see it?
Yes, sir.
Yes, sir.
Because it has just gone up on the slide. So log presentation. The scale at the top of the log shows negative. So normally the log presentation, the log which is what is the log scale in the case of density log? What is the log scale? Scale we have in the density and then gamma density log. What is the scale value? Maximum and minimum. Samir,
Yes, sir.
what is it?
For which
What
log,
is
sir?
density log? Gamma density log. What is the maximum and the minimum density value on the log scale? Kya bhai, Samir, you answered the question the other day and you forgot now.
0 to 3.
Huh?
So
What
for
is it?
density
Somebody?
3, sir.
Huh? What is this? What is the scale value?
Sir, 1 to 3.
No, 2 to 3. It
2
could
to
be
3, sir.
1.9 to 2.9 or 2 to 3. That is what we said.
Yes,
Not
sir.
1 to 3. What is the scale value normally in LDT, the litho density tool? The P values.
0
I
to
showed
20,
you
sir.
that. Huh?
0 to 20.
Not 0. You can say 1. 0 to hoga nahi re baba. But normally 1 to 20. Okay. Now, what is the scale value in the case of neutron log? It is saying, you look at it, it says negative. The scale at the top of the log shows negative minus 15% porosity on the right hand side. Okay, and 45% porosity on the left hand side. So the scale value ranges
Minus
from
15 to
45 on
45.
the left hand to minus 15%. What is it?
So minus 15 to 45.
No, it's 45 to minus 15. 45 is on the left hand side and on the
Yes,
right
sir.
hand side is minus 15. Okay. So
Yes, sir.
sandstones have an absolute maximum value of about 28% porosity. Shale porosity is much higher. Shale porosity is much higher, but because the grain size of shale is so small, oil or gas trapped in shale cannot usually be removed by drilling for it. So shale porosity is generally not important. Now, why is shale very important in SP log?
Sir,
Why
it
is
is,
shale?
it is an
Huh?
indication of the reservoir formation, sir.
No, it's good, but you are close to the answer, but you're not on the answer. I want exact. Remember, objective type question will have only a yes or a no on a very 100% bullseye. We
Yes, sir.
said that shale was impermeable formation.
Yes, sir.
In SP log, we said the permeable formation has to be sandwiched between impermeable formation. So the impermeable formation does not allow the hydrocarbon to migrate out. It's trapped there.
Yes,
Didn't
sir.
we say that?
Yes, sir. You said, sir.
So same thing. So shale porosity is much higher. Why shale porosity is there? Because shale is very less density, it's approximately 1.9 or 2.2 grams per cc, whatever it is, and its porosity is there. But because the grain size of shale is small, we know the grain size of shale is much small compared to the grain size of sand or grain size of limestone or whatever it is. So it is tightly packed. Okay, it's so small. Oil or gas trapped in shale cannot usually be removed by drilling for it. So shale porosity is generally not important. So shale, we are not looking for, generally we are not looking for a reservoir in shale. We are looking for shale for sure to act as an impermeable bed, so that your sandstone, which is a, has a good porosity and permeability, it's, and if it contains the hydrocarbon, it doesn't migrate out. Is that clear?
Yes, sir.
Very clear.
Yes, sir.
So, so we talked about the scale, just like we had a scale of gamma gamma density log, we have a scale of LDT log, now we have a scale of CNL log, and then we also talked about the importance of shale water. So you look at this over here on the right hand side, you have the CNL or the compensated neutron log. On the left hand side, you have the caliper log, I think so, caliper or the no, the you have both the caliper and the borole size, the bit size, sorry, the bit size is dash, and then you have the caliper, which is the borole, pretty much it shows pretty much no variation, and then you have the gamma ray. So you have the gamma ray, which is given in solid line, which you can see, and look at its relationship with the neutron log. When we said when the gamma ray count is more, what happens? When the gamma ray count is more means what happens?
Sir, it is an indication of shale, sir.
Shale, right? Am I right, Samir?
Yes, sir. Yes, sir.
So look at the top, the gamma ray count on the top up to a little below 1051 unit below that, it's more. And you look at your CNL log, the CNL log, the porosity is very small. But the next is when gamma ray count has gone down and perhaps it's a permeable bed. Okay, that means so it's gone down the gamma ray. So it is not having shale. Could be sandstone or limestone, whatever. You look at its this porosity value. Porosity value is, so there is, from these combinations you can have a look at. You can find out the value of uh, the porosity.
Porosity.
Yeah. Now we go to the. So we talked about the scale, we talked about the source, we talked about the receiver, we talked why we worked on the epithermal or thermal and not in the fast neutron. We talked about the hydrogen index, the limestone curve. We talked about the calibration. We talked about why limestone curve is used as the reference. Okay, with fresh water and things like that. Now we come to the depth of investigation, which is very, very important. So the depth of penetration of neutrons into the formation becomes smaller as the hydrogen concentrate increases. So what is happening? If the hydrogen concentration increases, that means there is presence of water or there is presence of oil. The H value increases. So obviously its penetration will decrease, because we have seen that with 18 collision on hydrogen, the energy falls down very drastically. Okay, so that's what it's talking about. It also depends on the source detector spacing. Yes, in general, it always depends on the source to detector spacing. And we had a very clear example of a lateral log versus a normal log. You remember that, Samir?
Yes, sir.
We talked about a normal log, 16 inch or
60 centimeters, sir.
64. 16-inch or 64-inch versus a lateral log which was 12 feet, whatever inch, 12 inches, 6 inches. Okay, and we
60,
said
sir,
if
60
we
centimeter, sir.
huh?
60 centimeter,
What is 60 centimeter?
24-inch, sir.
No, we had two normal logs, a 16 or 64-inch. You recollect that
Yes, sir.
versus a lateral log. Lateral log was what? How much? Was very long.
Yes, sir. 60 centimeter, sir. 60 inches, sir.
60, 60 inches, so 5 feet, right? 12
Yes,
by
sir.
60, 5 feet. I don't know what the value is, but I think it was very large. And why if you have the source to the detector spacing is very large, then what happens? Your depth of penetration increases, or your depth of investigation increases, but your resolution decreases,
Yes, sir.
right? So, in other words, the source to the receiver spacing is also an important factor. In addition to the amount of hydrogen present, the source to the receiver is also important. So it says that it also depends on the source detector spacing. The integrated pseudo-geometrical factor of the SNP, or the sidewall neutron probe, and the compensated neutron log tools are compared in terms of distances from the borehole wall for 35% porosity. So that is a standard. So for a 35%, so depth of investigation is 12-inch for CNL and 8-inch for SNP. So 12-inch means roughly what? 12 to 24 plus another 6, 30 centimeters. So it's the depth of investigation is about 30 centimeters. Now, what was the corresponding thing for gamma gamma density tool? What was it?
So 50 to 60 centimeters, sir.
Ah, so here it is almost half. You can see that. Okay. In addition to that, it depends upon the amount of hydrogen. So the depth of investigation is 15 to 25 centimeters compared to 60 centimeter there, varies with the tool used. Hydrogen index depth, it's a function of the hydrogen index and porosity. Maximum penetration in a tight formation with low hydrogen index is between 50 to 60 centimeters. So that means if you are, it's very tight and there is no hydrogen. Let's say you have a limestone, okay, and it's very tight and there is no hydrogen in it, be it water, be it oil, then the maximum penetration could be 50 to 60 centimeters. So it will be pretty much the same as your depth of investigation for your gamma gamma density log. Then we talk about the bed resolution. But you remember in gamma gamma density log, we said that if you can change the logging speed, you can bring it down to 15 centimeter in bed resolution. You recollect that?
Yes, sir.
Yeah. So let's see what happens here. So it says good bed resolution. Okay, two spacing are available: 20-inch or 26-inch. Two spacings available: 15.5-inch, 19.5-inch. Okay, SNP 16-inch. Forget about all that. So for a dual detector is normally of 10-inch, and it could be a dual detection could be 12-inch. So your bed resolution is roughly about 10 to 20 plus 5, around 25 centimeters or whatever, roughly 10 inches. So it's quite good. In other words, it's quite good. Okay, versus a 15 centimeter maximum we got in the case of gamma gamma density 2. Then we said that the factors which influence the neutron log, we just now said what are the factors? The factors which influence is the hydrogen index. We talked about sandstone and limestone having the same porosity but having different neutron counts. So it's also a function of the mineral type, and it is also a function of what we said, the clean sand versus clean limestone versus not. That means the presence of shale. So let's see what happens here. The factors influencing measurements is hydrogen, because yes, it's very sensitive to hydrogen which is present on water or oil. It is sensitive to clear micas, which is what we talk about as the shale. Okay, it is a function of the mineral type, and I showed you example of sandstone versus, you recollect I showed you example. Where did we have an example? And we had an example, you can see that water-filled sandstone with same porosity, limestone has different. So it's also a function of that. So it's a function of the mineral type. It has function of the neutron absorbers. Okay, it's a function of, I told you there is something called the neutron absorption log. That means when it dies down to a certain, it gets absorbed. Okay, so it's a function of the neutron absorbers. It's a function of the salinity. Why it's a function of the salinity? Because the reason is this. Let's see. Chlorine. Chlorine has. I just have the book in front of me. The chlorine has a thermal cross section of 33.2. So its cross section is very large compared to the hydrogen, which is 0.33. Almost 100 times. So this, if there is a water, if there is a formation which is having fresh water, or there is a same formation having the saline water, obviously it's a function of the salinity because of the chlorine. Because chlorine has higher cross section than the one which is non-chlorine. And then of course the hydrocarbons we talked about. The hydrocarbon and the hydrogen is pretty much same. Because both of them have hydrogen. Its only thing is how much of hydrogen is present. That's why when we talk about the hydrogen index, it's defined as the weight percentage of hydrogen which is present in the formation divided by the weight percentage of hydrogen in water, which is equal to 1. Hydrogen index is 1. But the hydrogen present in hydrocarbon is also important. Now just tell me now, does oil float on water or water floats on oil?
So oil floats on water.
Oil floats
Why
on
does
water
oil float on water?
because of the buoyancy, sir.
Buoyancy.
Yes, sir.
Karan,
Density.
अरे just now buoyancy बोल दिया, immediately density हो गया.
Yes, sir. Because of the buoyancy effect and just because of
Because
the
of the
density.
density बोलो रे बाबा, density बोलो, सीधा बात है.
Yes, sir.
So what
Density,
is the
sir.
density of oil?
Sir, 0.9, sir.
0.9, and density of water is 1, right?
1, sir.
Normally. So
Yes.
water floats on, sorry,
Oil floats on water.
oil floats on water, right?
Yes, sir.
Am I right? Okay.
Yes, sir.
So now when you are going to do an exploration, what I'm sure you're going to look for the oil water contact.
Yes, sir.
Obviously you're going to look for the oil water contact. Let's say it was an anticline and you have an oil water contact. Okay, so the oil is floating on the water. Your object should be, you should be in the middle of the apex of the oil. If you're going towards the side, you'll be hitting the water. So that means you have bypassed the oil, right?
Yes, sir.
Yes, sir.
Okay, so that means if you look at it from here, the neutron law can be used as a good tool to find the oil-water contact, because for salinity, because of presence of sodium, which has a larger cross section, has a different response than the hydrogen which is present in the water. So it acts as a good indicator for the soil, for the oil-water boundary. Is that clear? It can be used. I'm not saying
Yes, sir.
it is or it can be used. Is that clear?
Yes, sir.
Okay. So now what is? So we will talk about the hydrocarbon effect tomorrow. Not tomorrow, Tuesday.
Yes, sir.
Yes, sir.
So is everything clear now? I'm always making a comparison between LDT, gamma, and neutron so that it gets into your head, Re Baba.
Yes,
Because
sir.
all of them are radioactive. When we come to sonic is not a radioactive. Is that clear?
Yes, sir.
हाँ तो घर समीर अभी तुम
Yes, sir.
खाना खा के टीवी मत चलाओ थोड़ा go over this whatever we studied. If you're not able to understand, go थोड़ा online में जाओ देखो ना, so many presentations are available, all the answers are available. I've seen so many presentations are there from college students. Chota Mota college like Surgapur, so many presentations are available by students uploaded. Have a look at all that and get your fundamentals clear so that you can do good in the exam. That's all I want. But now if you switch it off and then immediately khana khao, एक टीवी सीरियल देख लो, सो जाओ, gone. Then nothing, nobody can help anybody. Is that okay?
Yes, sir.
Asma बोलेगा I have to cook, so sir you have to excuse me. Asma वो बोलेगा. Namrata is there.
Yes, sir, I'm here.
Namrata is lucky her mother is going to cook. So that is Asma, your mate is coming or not allowed?
Just this month, sir. Like past
Yes.
2-3 days.
Now mate is coming or not?
From the past 2-3 days only.
She's coming.
Yes.
Okay, so no, that means you don't have to cook. So you also fall in Samir's group.
Not cook, sir. No, I do have to cook.
I thought your maid is cooking.
No,
Acha,
sir.
you are cooking. Acha, you are cooking. Good. So after cooking is over, thoda ye dekh lo, or before cooking is done, is cooking over or you're going to cook now?
Sir, I have to cook every meal time,
Oh.
so
Okay, theek hai. Thoda go over it. What I'm saying is when it's fresh in your mind, go over it, spend some half an hour for 45 minutes, and it will stick on you. And always make a comparison like I'm making.
yes.
Because you never know. If Sagar decides you're going to have an objective type of question paper, you're going to have a tough time. I'm telling you that. Okay?
Yes, sir.
Okay. Samir, so yaad
Yes, sir.
rakho re baba.
Yes,
So
sir. I have seen some videos.
So video, the next time when I ask you a question, you should answer on the dot. You should not, I'm asking you about the receiver, you're talking about the source. If I'm asking you about density, you're talking about buoyancy.
Sir, I was confusing some detectors and sources,
Don't
sir.
get
That's why.
confused till you do good in the exam and
Yes, sir.
get a job. After the job, get confused. जॉब मिलने का है रे बाबा, ठीक है?
Yes, sir. Yes, sir.
ओके ओके, ठीक है, बाय.
Thank you, sir.
Okay, welcome. If you have any question, you can jot it down and ask me. If I know, I'll answer. If I can't, then I will go through it and answer it again. Any question that you have, you can always please feel free to answer. Ask me. Okay.
Yes, sir.
Okay.
Yes,
Bye.
sir.
Bye.
Thank you, sir.
Bye.
Bye.
Thank you, sir.